Hello, Lucia. Welcome back. Welcome back to me as well. Today we're going to be solving yesterday's contest, the weekly 369. I shared the link in chat. And let's get started. So, the first one, Q1. Let me share the link as well. This one is an easy. It's called find the k-or of an array. So you're given an array nums and an integer k, and they define this operator. Creepypasta, welcome. This operator k-or of nums. Thank you. Is a non-negative integer that satisfies the following. So the ith bit is set in the k-or if and only if there are at least k elements of nums in which the bit I is set. And we're asked to return the k-or of nums. And here we get the definition of what a bit I is set. Alright, so we have 3 examples. This is a small array, 50. Remember always to check the constraints before you decide what algorithm to use. But in this case, the algorithm, we just need to implement what is asked in the, as usual with easy problems. So let's work out an example so that we get a feel of what we're asked to do. So let's see. This example number 1. Let me see. So we can think about this as a table. So here the biggest number is 15. So we're asked to handle bits, so it's better to write the numbers in base 2. So we can think about this as a table. So this is a little thick. Oh, let me retry this. Okay, so we're gonna have the 0 position 1, 2, and 3, because the corresponding powers of 2 are, so 2 to the 0 is 1, 2, 4, and 8. And since we got up to 15, here we don't need anything bigger. So we have 6 numbers. So there we are. So again, we can think about a table. So here we have the 7, 12, 9, 8. The order doesn't matter, but I'm following the order that we got. And so here 7 is 4, 2, and 1, right? Then 12 is 8 plus 4. So we are just exercising how to convert numbers into base 2. Here 9 is going to be 8 plus 1. Then 8 is just an 8. It's the power of 2. 9 again. And finally 15 is altogether So it's 8. So we have 12, 14, and 15, right? So this is the table that I mentioned. And we're asked to compute the sum of the ones on each column, right? So here we have 4. Here we have only 2. Here we have 3. And here we have 5, right? And so then we ask, so k here is 4. So in this case, we have 4, which is greater than or equal to k, is not, 3 is not, and 5 is greater than or equal 4. So this is our answer, which is called the k-or of this set of numbers. And if we translate this to base 10, again, this is an 8 plus 1, so it's 9. So that's why this is the answer. So we worked out the answer. So now we need to know the bitwise operations to do what we did. So in this case, the numbers are less than 2 to the 31, right? So here we had numbers that were less than 2 to the 4. 2 to the 4 is 16, right? So that meant that this variable here went from 0 to 0 to 4, from 0 to 4, without including 4. So if the numbers are less than 2 to the 31, then the indices are going to in this range. So let's call that the column. So for column up to 31, here we're gonna store the result, and then we want to go for every number in nums, and now we want the let's use I, which is a variable name that they use here. So we want the ith bit of x. So for that, we can shift the number I times to the right. So that means that the bit that we care about, it's going to be in the least significant place after the shift. So then we AND it with 1, and we're going to isolate that bit. Every other bit that could be to its left is going to be zeroed. So we get this bit, and we're gonna add all the bits for this column, and then we check the condition. If it is greater than k, greater than or equal to k, then we have to add it to the result, and that means that we just OR the ith bit, because that means that in that column we need to set a 1. Okay, so this should work. So we get the expected answer for the examples. Are there any edge cases? I don't think so. So let's submit, and we get accepted. All right, so this is a standard way of getting the ith bit, so it's useful to learn it. let me share the link to my submission. But yeah, maybe so this solution is very easily translatable to C++ or Java or other languages. So I've been asked to do solutions in other languages as well, but I rather only use Python, but sometimes I try to make implementations that don't use things that are not in other languages. So this is this kind of solution, but we can use the Python things, and since we are only adding here these values, we can use the sum function, and here we simplified it a little bit, and we can even get rid. So now cur is only used once, so we can put it here. So this is pretty mechanical. So instead of ORing, we can do a sum, since all the bits are exclusive. There's no intersection, so we can turn this into a one-liner like this. And we get accepted. Cool. So yeah, that's a little Python magic, but you could see that everything I did was just change the loops for the calls to sum and move the conditionals. So it was pretty mechanical. Cool. Yeah, thank you, Lucia. All right, so let's move on to question 2, which is a medium. But usually Q2 and Q3 are mediums, but Q2 is easier than Q3. Okay, so minimum equals sum of two arrays after replacing zeros. You're given two arrays, nums1 and nums2, consisting of positive integers. You have to replace all the zeros in both arrays with strictly positive integers such that the sum of elements of both arrays becomes equal. Return the minimum equals sum you can, or -1 if it is impossible. And we get 2 examples. Okay, so, and they're up to 10 to the 5 elements, and the values are up to 10 to the 6 and non-negative. So, well, here in example 2, so yes, the sum, here there are no zeros in nums2, so the sum can only be 5. And here, since we know that we have to replace zeros with positive integers, strictly positive, so the minimum that this can sum, if you replace the zeros by ones, which is the minimum, you get 6, which is already greater. So that's why it's impossible to make the sum of both arrays equal. And here in example 1, there are zeros in both arrays. So yes, I think this is the only case when if you have at least a 0 on each, then you will be able to get to get an equal sum. The only case is when there's at least one without zeros, then you might get to this case, the -1 solution. So I think the way to think about this problem more in a principled way and trying to avoid special cases is to think in terms of well, let me show you. So here, so the first observation is that the array really doesn't matter. So another way to, so nums, oh, this keeps changing the width. So nums1, we can translate the input in a way that only saves the information that we care about. So we only care about the sum of the array. So here it is 6. And how many zeros it has. So here it has 2 zeros. And nums2 has some 11 and has 1 0. So we can forget about this. It doesn't matter. Only these two numbers matter. And so here, what is the minimum number that you could have in this? So it's already at the sum is already 6, but you have 2 zeros, and the zeros can be 1 each minimum. So the minimum that it could sum is 8, and then the maximum is not limited. There is no limit. So you can think about this as so this is a way to represent this. And here again you have 12, and there's no limit to the maximum. So now we want to find the intersection of these two intervals, and one way to do the intersection of intervals programmatically is just to get the maximum of the left limit and the minimum. So here the maximum is going to be 12, and the minimum of this is infinity. So this is the interval of the intersection, right? And the minimum, so, and the minimum value here then is going to be 12. And that's why the answer here is 12. So we can do this without having many special cases by thinking in terms of intervals. So we can do the translation that we did. So get interval of nums. So we have these two numbers, the sum and the number of zeros, which is going to be this, and we can use the count function in Python, but it's just counting the number of zeros. And then we have two cases. If there's 0 zeros, then so let's say that it is closed and open. So these two numbers represent the interval, and otherwise this is going to be this and infinity, right? Because every 0 has to be at least 1. So this is the minimum value. Okay, so this is the same that we did before. So now we have left and right of get interval of nums of 1, left to write 2 of get interval of nums of 2. And now we have left and right of the intersection, which we said was the maximum of the left and the minimum of the right. And now we want to know if the interval is empty or not. So if left is less than right, then it is not empty, so we return left, which is a minimum sum in the intersection, the minimum value in the intersection, and otherwise we return -1. So as you can see, the logic is very easy to follow because we solve it in a principled way. We translated the input into an interval representation, and we used the knowledge that we have about how to calculate the intersection of intervals. And so we don't have to think about special cases, and it's accepted. Interesting to view it as interval intersection. Yeah. I think it's good when you can import. You can find a way to represent the input as an object that you already know, so you can import the knowledge. All right, so that was good. Here's the submission, in case you want to take it out. And let's move on to problem number 3. Minimum increment operations to make array beautiful. You are given a 0-indexed integer array nums having length n and an integer k. You can perform the following increment operation any number of times including 0. Choose an index I in the range 0 to n-1 inclusive and increase nums of I by 1. So an array is considered beautiful if or any subarray of size of 3 or more, this is interesting, its maximum element is greater than or equal to k. Return the integer denoting the minimum number of increment operations needed to make nums beautiful. Subarrays are contiguous. Okay, the definition of subarray, we get 3 examples. So the size is 10 to the 5, so we cannot do a quadratic solution. And then the values are up to 10 to the 9. So yeah, the first observation here, so we only care if a number is greater than or equal to k. So already, if a number is greater than k, it doesn't matter, right? So we are not going to increment that number, and it's already greater than or equal to k. So in a sense, we can think of the array in binary, because we have the elements that are greater than or equal to k and the elements that are not. And it only matters, the only subarrays that matter, if they have, if the subarray has an element that is greater than or equal to k, then it's already beautiful. So we only care about the subarrays that are within a streak or a group of elements that are not greater than or equal to k. So, but then we have this thing that is not easy to decide which ones How it's possible this problem is a medium and the first one was easy? This seems more math basic oriented and the first one a bit more tricky. You mean the Q? You're comparing Q2 and Q1? You think Q2 is easier than Q1? Creepypasto. So I think so Q1 and the first one was easy. So the first one, I think yes, you need to know about the bitwise operations. But if you know that, I think that's knowledge that is assumed from the participants. And if you know that, it should be straightforward to implement this. There's no observation needed, no insights needed. Whereas on this one, you do have to you have a decision to make, because you need to replace the zeros by some number which is not in which you don't know how much it should be. So I think Q2 is more difficult in that sense, that it's not just implementing something that you're told. You have to make decisions that are non-trivial. Anyway, so going back to Q3. So what was I saying? So yes, I was saying that the intervals. Yes. So here you have to make a decision of which ones to increment. Of course, if you are going to increment one, you of course should increment it till it gets to k, or not at all. Of course, you don't. It doesn't make sense to stay halfway to k. So, but it is not clear, because maybe if you go from left to right and you have to decide, so do I increment this the ith value, for example? Well, maybe it's close to k, and then you say yes, it's worth it, but then maybe the next one even closer to k, so it was better to not increase and increase the next one. So there are some decisions that it seems that you cannot make greedily, because there's a trade-off between how close it is, but then what the position is in the array. If it comes a time, suppose that you decide not to increment one, and then not to increment one, but then you're going to have a streak of 3, and that is not allowed, because if you have a subarray of size 3, then it's not beautiful. So what do we do when the greedy choice is not possible? Well, we can do dynamic programming. Okay, so we can do what sometimes is called take it or leave it. So we have to decide whether we increase the current element or not. So that has the structure of a dynamic programming solution. But there is a catch, because of what I was saying, that if you decide not to increment it, then you start accumulating a streak, and at some point you are forced to increment it, because otherwise you'll get a streak of 3, which is not allowed. So if we go here, we can think about, so the mean, I keep getting this. Okay, so the mean increments, let's call it, and we're gonna have the ith position, the position in the array, and then let's call this the size of the streak. And so if I is greater than or equal to n, it means that we went over all the elements. So there are we need 0 increments once we got to the end. Then if the current position, so if, how is this called, nums? So if nums of I is greater than or equal to k, then we don't have the choice to increment it, right? We just move on to the next element, and whatever streak we were accumulating, we just reset it because we found an element that breaks the streak. And now if we are at this point, then there are 2 possibilities. If the streak, so if the streak is 2, then we are forced to break it. So that means that we need to increment. So the number of increments is going to be increased by k minus nums of I. Let's abbreviate it that way. But otherwise, we have 2 cases. So we will have minimum of the case where we increment it, and the case where we don't increment it, so we increase the streak by 1. Right? So this is the solution, the recurrence. So we use the cache notation to do memoization. So min increments. So remember to use, I really recommend you to use so we said this was I, and the streaks which start at 0. I recommend to use, so we can abbreviate this, min inks. But don't use the name DP or something that is too generic. I prefer to use the name that declares what the value is. So it's better than to think about the recursion when the name of the function has meaning. So here, so if we are here, we said we return 0. Oh, streaks, thank you. So yeah, it's not plural. So streak. Okay, so then we have the case where nums of I was greater than or equal k. In that case, we cannot, it doesn't make sense to increment, so we just move on to the next and we reset the streak. And here we have the option of incrementing, which it's going to be k minus, this is the number of increments that of increment operations that we need to get nums I to k, and we reset the streak. But if the streak is less than 2, then we also have the option of keeping it as it is and increasing the streak by 1. And that should be it. And we get the examples right and accepted. Cool. Thanks for the correction. So yes, this is pretty much the same as we did here. Nice, thank you. So, well, yeah, but these two cases we handled together. So in math notation, sometimes it's harder to do this kind of if statements, but I think in the code it's better. So yes, so let's move on to the last problem. Maximum points after collecting coins from all nodes. So yes, we are given an undirected tree, rooted tree at node 0 and nodes, and then yes, we get the edges in the standard way, and then we are given an array called coins of size n, which indicates the number of coins in the vertex I. And then we also get an integer k. And starting from the root, you have to collect all the coins such that the coins at the node can only be collected if the coins of ancestors have been already collected. All right. Coins at node I can be collected in one of the following ways. So one way is to collect all the coins, but you will get there's the notion of points and coins, and the points are calculated by this expression. In this case, it's coins of I minus k, which can be negative, so you can lose points when k is bigger than coins of I. And the other way is to in which in this case you get coins of I divided by 2, but the catch is that because, well, this does not depend on k, right? But so if k is big, maybe this becomes negative, and in this case you'll get a positive non-negative points, so it might be better, but then all the nodes in the subtrees get also divided by 2. So that's the catch. So at each point you need to choose which one of these two points schemes you choose. And you need to return the maximum points that you can get. There are up to 10 to the 5 elements, and here we get a couple of examples. So here, collect all the coins from node 0 using the first way. So the first way, we got 10 coins at node 0, and k is 5, so it's 10 minus 5, so you get 5 points here. But then you go to the child, node 1, and again you have 10 coins there, and they're using the first way again, so you subtract k, and now you accumulate, you gain 5 more points, so you accumulate 10. Then here, this is supposed to be the optimal way, so here you use the second way. So now you divide the 3 coins by 2, rounding down, so it's 1, so you accumulate 1 more coin. But now the number of coins is in 3 is also 1, and you use the second way again, otherwise you'll get a negative number. So you don't get anything here, you get 0, but if you use the first way you'll get a negative, so that's why it's better. And that's so then you finally accumulated 11 points. And that's the optimal. So this is similar to what we did before. So at each point you have 2 choices. You use the first way or the second way. And so by using dynamic programming, you can try both and see which one is better. The catch here is that you need to remember how many times you use the second way. In all the ancestors up to the current node, and that is potentially a big number, right? Because it could be, so the path from the root to the current node could have all the nodes. If it's a long path, it could have up to 10 to the 5 nodes, and so the number of subproblems will be determined by the node, the current node, which is 10 to the 5, and then all the times that you divided by that you use the second way, and that would be quadratic, and it would be too slow. There would be too many subproblems to solve. However, here's the key observation, is that since you are dividing by 2, you cannot so the values here are up to of the number of coins are up to 10 to the 4. So you get to 0 pretty quickly by dividing by 2. If you divide by 2 around like 15 times or something like that, so 2 to the 20 is already 1 million, which is bigger than 2 to the 4. So you're going to get to 0 pretty quickly. So you only, once you get to this number where you always are going to get 0 points, then it doesn't matter if you keep incrementing, you keep choosing the second way. You just have to keep. Hey, I ask Heaven, thanks for the subscription. Thanks a lot for the support. So the catch is that so here we have, if we have 2 to the 14, if we divide by 2 14 times, then we will get 0 always, even if we get, so this is the max D. If we call D the number of times we divide, is going to be 14, right? So now, in order to traverse the tree recursively, to do the memorize function, we have to translate the, so n is the number of nodes. We have to translate the edges into an adjacency list. So this is very standard code. So we go all the edges, and we, since this is undirected, we just add the edge from U to B and from B to U, and then we are going to do the cached function, which gives me the maximum points, the current node, let's call it U, then the parent, so that we don't go up the tree, which initially is going to be -1, and then we want to count how many times we use the second way, so that we divide by 2 those many times. Initially is going to be 0, right? So eventually we're going to return the maximum points starting from the node, from the root, which it's node 0. So here we have 2 options, right? So let's call them res1 and res2, and finally we're going to return the maximum of both. So the adjacent nodes are these, but we want to make sure that it is not the parent, right? And we're going to go over the children in both cases. And here we are going to use the first way, which going to call max points for the children B. The parent is going to be U, and we're gonna keep D as it is because we're using the first way. And for the coins in position U, remember that we need to divide by 2 D times, which is the same shifting the shifting coins of u to the right, and we have to subtract k. So this is how much points we get in the first way. Then on the second way, we are going to have the d2, the next d, it's going to be d2, and we are going to call again, but now with d2 because we have incremented it. And here we'll get the coins, and it doesn't depend on k, and that should be it. We get the right answers for the examples. And it's taking a little long, but I think this should be, oh no, we did not, we did not use the, I did not use the max d, that's why it failed. That's good, makes sense. So max d, so if we get, at some point we get to 15, we're gonna keep the 14, because it's going to have the same effect as we shown. It's going to make this 0, so it doesn't matter, and that's going to make the number of sub problems manageable. It's going to be, so there will be 15 possible values for d, so from 0 to 14 inclusive, and then u has 10 to the 5 possible values. So 15 times 10 to the 5 is a small number. So, well, it was good that we tested that was slow, so that we proved that with this change it becomes fast enough, and that's it. Cool. So yeah, that's it was not planned, but it was interesting to prove that. So that's my submission, and that completes the contest. I don't think these problems can be done more efficiently. So yeah, that's all I got. I hope you learned something from this. And so I'm back doing streams. I'm gonna be doing like the simple code. Thanks. Yeah, great. Yeah, I think the code ended up pretty short, which is usually good if you don't obfuscate it. So yes, that's all I have. So thanks you for watching. Thanks for the support, and thanks for the subscription. I really appreciate it. So bye bye.